Hi, this is our last video on analysis of this question, that is a laminar flow. And today we want to do some post process using CFD post. We are going to generate these velocity vectors and contours. Then I'm going to create this chart that is a comparison of fluent solution versus analytical. The formula used to get to an analytical solution is this formula. As you can see, when these two are the same, it means we are at the boundary, we are getting a zero velocity. But at the center here, this term becomes zero, we get 2. Therefore, the value is supposed to be 2 at the center, but 0 at the boundary. You can see here. Okay, let's now open the CFD post. You right click on the results, you say edit, so that we can start CFD post. Once you open a CFD post, this is what you get. Remember, the CFD post uses 3D, doesn't use a 2D. The reason why, you can say we have this surface. It takes the first surface, you can see we have a periodic one, this surface, and revolve a little bit to get a shadow. You can see here, but that's fine because CFD has to use 3D. Therefore, first thing we need to understand the velocity magnitude contours. If you go to the contour, you can say this one is a velocity magnitude contours. For the geometry, I want to use our domain over the whole full domain. Location, I want to use this surface called periodic one, this surface here. And the variable is velocity. I want to use average velocity, that is velocity. But in this case, velocity and velocity u have the same value. If I say apply, let me zoom in a little bit and see what happens. You can see at this point we are almost getting a 0, but at the center we are almost getting 1.98. We are almost getting a 2. If I can increase the contours to 50 and apply. I like using full model, even the bottom side. Therefore, I can go to I want to mirror this one to get the bottom side. Therefore, I can go to the default transform. First of all, hide this. Under the default transform, double check instancing information from domain so that we can apply refraction along XZ plane. You can see now we have top and bottom side. Then activate this. Now this one is like it looks similar to this, top and bottom side. You can see how the contours look like. Let me do the pressure contours again. Let's click this one, duplicate, call it pressure contours. For the deselect velocity, make sure the pressure contours is active. But for the instead of velocity, use pressure and apply. As you can see, the pressure at the inlet becomes 5 pascals. Remember initially we had defined as 0 the guess when you are defining the boundary conditions, but as the flow progresses, the pressure is reducing, meaning the pressure is used to push the liquid through the pipe. Therefore, the pressure behaves as expected. Um, if I go back to the velocity, if you want to know the velocity at any given point, you can probe using this probe here. I want to probe, you go to other velocity u, say okay. Therefore, if you select this just any place, you can see the value of velocity. You can see now I'm selecting, if I want to probe here, I can see on the bottom we're getting 1.8. At this point I'm getting a 0. This point um this point I'm getting 1.955. Yeah, that's how you can use probe if you want to probe a velocity along your plane to get any value. In case you want to save this image and you want to rotate this legend, double click the legend, use horizontal apply, then you can use this icon here, save picture, then the save, then to take a screenshot and save. Let me go back to the vertical, apply. Okay, next let's do velocity vectors. I want us to see whether our velocity vectors will take this shape. You see, for a fully developed region, it should be look like a parabola like this, but this one is not fully developed. Let's see whether we can get this type of vectors. I need to do, you select vector 1 or velocity vectors, that's fine. Then I need to create to define location. Therefore, if you double click velocity vectors, where they, let me see, let me fast forward hide this. Let me select again, or you have to say apply. Okay, we need not to select location. First of all, we need to create a location where we want our velocity vectors to be. Because now this is a vector. If I say location, if I select inlet, apply, if you say hide, this is what we get. If I select periodic 1, apply, let me zoom, this is what we get. You can see what we are getting vectors. If I use a small symbol, 0.1, apply, this, you can see the vectors we are getting here. Maybe go to geometry. We are using a variable of velocity. You can scale this image if you want to scale here. We go to scale by 4 to make it bigger, like that. But for now, it's not necessary. I want to create 2 locations, one at the inlet. Therefore, I need to create first location line here. Call it inlet. Inlet is at 0 here with a height of 2. I'm creating a line. You can see my line here at inlet. Let me create another one near inlet. and give it 0.2, apply, another one there. Let's create another one called middle, that is 1.5, 1.5, apply, versus 1.5. If you zoom in this one here, you have a middle one. Then we need another one near the edge. At this point, let's create another one all at the edge. Let's do at the edge outlet. Call it outlet. And for the outlet, use 3 because the length is 3. Then for the velocity, these vectors here, I want to use location here. Location, I want to use the ones, these 3, these 4 of them, like that, apply. Then for the arrow, I want to use a 3D arrow 3D, size, let's see, size of 5. That's so big. Okay, for domains, I'm using a variable, I'm using a 3D. Okay, for the line here, these lines, you have to use 50. Yeah, let's use 50. Everything to be 50, 50, 50. Also this 50, let's use 50. Let's use 50, apply. Okay, let's now see what happens on near inlet, 50, apply. For the near inlet, supposed to use 0.2 and 0.2. Yeah, let's now do comparison with the analytical solution. Okay, as you can see, at the inlet, we have some similarity, you can see. This one is a near inlet, you can see some similarities here. As you go to the outlet, let's see the outlet here and see some similarities. You can see we have a fully developed flow. We have some similarities here. Therefore, we can see that the liquid flows using a parabolic shape, similar to this profile. This is the equation, the profile. Yeah. And if you not plot, I can plot this this profile. Let me zoom in. I want to see whether I can plot this profile. To do that, you select the chart. I want to select velocity outlet chart or outlet profile. For the data series, let's use the series 1 for now. Now our series 1 here, we need this location, that is an outlet location. Therefore, you select here no, let me, this series here, I want to use the location to be outlet. If you apply, um, let me say, for the x-axis, you can see we have a weird graph. For the x-axis, I need velocity to be here, not count. Therefore, I need velocity. If I apply, then the y-axis to be against radial direction. When I say radial direction, this one is along y-axis is my radial direction, and this one is a velocity. Therefore, here I need radial. Okay. For the line display, let's first of all leave everything as default. You can see now this one is a parabolic one, almost reaching at point of 2, but this value is 1.98, as you can see from the graphics representation. Because of the mesh, if you refine the mesh, remember we used 100 divisions and 10. If you refine the mesh, you might get 1.999 or a value that is closer to 2. And remember the residuals, we used e to power 6. If you increase that value, also we get a more accurate uh, analysis. Okay, now going back to the profile here, first of all, I want to do comparison. I'm going to attach. You can generate an Excel format, Excel file for using this equation, but I'm going to attach it for you, and you can import it here if you want. I will attach this file for you. For the series 1, I'm using an outlet location, but for series 2, I'm using a file called epipe for the fully developed analytical approach. If you apply, you can see now this one becomes my uh, 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 for the analytical solution, that is blue. General, I can say now this one is a velocity. The title is velocity profile. That is the title. Data series, we have already defined the data series. Along the x-axis, I want to use for the, instead of velocity, I want to use axial velocity, so that we can add some units, meters per second. You can see axial velocity, that is for the x-axis. Y-axis, instead of using ym, I want to use r to represent radial direction in meters. Apply, yeah. Line display, this fine. Let's see the chart. For the chart, I want to use a bigger size of line. For the chart, I want to use 3. Then for the font size, I want to increase it a little bit to make it more presentable. Apply, yeah. Then for the line display, instead of series 1 and series 2, for the red one here, I want to use name called, I want to use Fluent solution at outlet. For the series 2, untick this one and write analytical solution at fully developed region. If you apply, now the graph is well presented. You can see how our graph looks like. Red one is our fluent, but analytical one is this value. You can see we have some errors here. This will depend on your parameters at mesh level, residual parameter, and coefficient of drag, because those are the parameters you defined for the convergence. Okay. I think we can stop there. I will create another video to go a little bit to go in depth on the concept I was not able to explain in my next video. We are going to do some simulation here to see the liquid flowing and show how you can define your own equations, expressions here. I will illustrate how you can create a video to do some simulation. This one was just a basic introduction to CFD. I can say thank you for your time. Share this video with others to learn, and see you in my next video. Thank you so much.